And in the previous lesson, we looked at elements and compounds and mixtures. And in today's lesson, we're going to look at the first type of bonding, and then we're going to cover 4 types of bonding, but the first one will be metals and metallic bonding. We're going to see how metals get their properties from this particular bonding structure. And here we have a variety of metals. Hopefully you can recognize some of them. You can see that some of them are different, but these properties that we're going to talk about will all be the same among most of these metals. So metals. Pure alloyed metals have special properties that are often exploited in industry. That's pretty obvious. We see metals used all the time. Cars, building structures, you name it, it's probably made out of metal. And the reason is they have special properties that allow us to do things. Electrical conductivity is one of them, major one. Strength, malleability, ductility are all really valuable properties that industry likes. Electrical conductivity is great for us as humans because we really like using electricity for things. Strength is good because we like, building buildings bigger. We like planes moving really fast. Malleability, we like to make these things easily. And ductility is, drawing out wires to use in our electrical systems. So all of these are quite useful properties, and that's the properties that most metals possess. And these properties can give us insight into the structure of metals. The properties kind of infer certain details about the metals, but there's more to it than that. So the metal structure, what is the metal actually? Well, the metal consists of a 3-dimensional lattice of positive ions, and these are the nuclei of the atoms, surrounded by a sea of delocalized electrons. There's a lot of words there, but the key thing is that you've got a lattice, essentially, of these positive ions. So if you imagine it going into the board as well, you'd have like circles going into the board as well. And that's what we call a 3-dimensional lattice because it makes like a 3D shape. And the nuclei of the atoms are all positively charged because they have protons inside them. Now the key thing is that the electrons in the outermost shell, the valence electrons, so to speak, they're not bound to any particular atom. Okay, so this electron doesn't belong to this atom. And that's what we mean by delocalized. They don't have a set location. So they're free to move in whatever direction they want. And that has particular implications for its properties. So you can see that each of these electrons is moving in different directions, random directions, and they're not bound to an atom. So that gives it unique properties, and we'll talk about that in a sec. Now it's the attraction between the positive nuclei and the negative electrons that keeps the crystal together. The fact that this electron may be attracted to this atom sort of keeps the lattice from repelling itself apart. That helps to keep it together. Now the delocalized electrons, let's look deeper into what that actually means. So instead of having the circles, we're just going to have the minus signs because it's a little bit easier. So delocalized electrons are the valence electrons of the atom, like I mentioned before. Now, since metals only hold their valence electrons weakly, so you should know that like sodium wants to always get rid of its electron, its valence electron, most metals will only hold their valence electrons very weakly. These outer electrons are then free to move through the lattice of the material. So they're happy to move between the ions however they please. Now that's why metals are excellent conductors. Just think about that for a second. If these electrons are free to move wherever they want, if we apply a voltage across them, then the electrons will all be attracted to the positive end of that voltage. And then they're free to move to that voltage if they want. So that means that there's this big movement of electrons, which means there's a big movement of charge, which is essentially what electricity is, just the movement of charge. If you see that all these free charges are allowed to move to the positive end, means that metals must be excellent conductors because those electrons are all free to move. And if you look at it, metals are all good conductors, or most of them, are very good conductors of electricity. So that this model really helps us to explain the properties that we see in metals. The electrical conductivity we've just explained, but what about ductility, malleability? How come they exist? Why doesn't the lattice explode into a million pieces when we hit it, like a diamond does? Why does it just bend and warp? So that's our next question. Because each of the ions is really closely packed, because it's a highly dense material, the nuclei are very close together. The nuclei, so these guys, are quite close together. Now, since the electrons aren't bound to any particular atom, layers of atoms can actually slide past one another while still being bound to the structure. Here we got the normal lattice. This is just a plain metal. Then we've applied some kind of force to the top half, hit it with something. And you can see that the top half can actually slide across, but it still remains attracted because there's electrons in between. So the electrons in between are actually holding the lattice from falling apart, but it's allowed these top ions to actually move across and slide. And that's why metals are ductile, because if we can slide and rearrange the atoms accordingly, we can actually form new shapes. And so that's why they're malleable. Or in the ductility case, we can draw it out, sort of stretch these layers and hopefully get them to collapse in on each other, and then you get a wire. These delocalized electrons actually help to keep the structure while it deforms. So the electrostatic attraction between metal ions and electrons is still held, even though the atoms are actually moving past one another. And this obviously gives the metals good malleability and ductility. So that concludes today's lesson on the metallic bonding and metals. We looked at the metal structure, what delocalized electrons are, and why that has implications for the metal properties. Okay, so we'll move on to the question segment. Hopefully you can develop your knowledge, or at least expand it with these questions.